Let's talk about Newton's laws of motion and why they are important. From the flow of blood in our vessels to the complex dynamics of rockets, satellites, planetary motion, moonwalk of Michael Jackson, and even the Irish dance of Jack and Rose in the movie Titanic are all governed by the laws of motion. Buckle up and let's blast off to the world created by Newton. This book is The Mathematical Principles of Natural Philosophy, or the Principia. It is perhaps the most important scientific text that has revolutionized how humans perceive the world around them. But what is so special about it? To understand that, we have to go back to 1543. Nicholas Copernicus proposed that the sun is the center of the universe and not the earth, which was the conventional wisdom at that time. In the following years, Galileo, Descartes, and Kepler, among many others, laid foundation to this new science, which would be able to explain the heliocentric universe and would also replace centuries-old Aristotelian worldview. In Principia, published in 1687, Sir Isaac Newton created that new science. He not only created it, but he nailed it. All in all, Sir Isaac Newton answered a question that has gripped human mind since eternity. That is, what are the laws that govern continuously evolving systems? I think the best way to learn Newton's laws of motion is to ask series of connected questions, one leading up to another. We've all been curious about how and why things move, and therefore the first question is how to mathematically describe motion. And once we learn how to mathematically quantify the amount of motion contained in an object, the next question is, if left alone, what would an object do naturally? And as we'll see, the natural tendency of an object is to not do anything new. That is, they are inherently lazy. Now, given that the object is inherently lazy, how do we bring about a change in its state of motion? And that is our next question, and this brings force into the picture. And this leads us up to the final question on what is the origin of force. And as we'll see, forces exist in pair of an action and a reaction. Let us start with our first question. How do we quantify the amount of motion contained in an object? And to do so, let us consider an object that is traveling in the straight path, and this object has mass and velocity. The mass of an object is a scalar quantity because it can be quantified by a single number, whereas velocity is a vector quantity, and the magnitude of velocity gives you the speed at which an object is traveling, and the direction of velocity gives you the direction of motion. Let us now consider two thought experiments, and our goal is to make two very crucial observations about motion through these experiments. Firstly, let us imagine that you have a heavier object and a lighter object parked together. We'll all agree that it will take much greater effort to push the heavier object than the lighter object to bring them to the same velocity in a given interval of time. On the flip side, if you have a heavier object and a lighter object both traveling at the same velocity, it will take much greater effort to stop the heavier object than the lighter object. For the second thought experiment, let us consider two objects with same mass. And in this case, the object traveling at a higher velocity contains more amount of motion and therefore requires greater force to bring it to stop. Based on these two thought experiments, it is clear that the motion contained in an object depends on its mass and velocity. It is now time to introduce the main character of this video. Momentum. Momentum is defined as the product of mass and velocity, and it is a vector quantity. The magnitude of momentum gives you the amount of motion contained in an object, whereas its direction, which is same as the direction of velocity, gives you the direction of motion. Now that we understand how to mathematically describe motion, in the next question, we'll explore, if left alone, what would the object want to do naturally? Or, what is the natural tendency of the object towards change in its state of motion? Through his experiments, Galileo Galilei observed that the natural tendency of an object is to resist change in its state of motion. Sir Isaac Newton formalized this observation into his first law of motion, which states that the object continues to be in a state of rest or the state of uniform motion along the straight line unless compelled by a net non-zero external force to act otherwise. What this means is, if the sum total of all the external forces acting on the system is zero, then the object does not want to change its state of motion. Or in other words, the momentum of the object does not change. Mathematically, what this means is, the time rate of change of momentum of the object or the system is zero if the net external force acting on the system is zero. And this observation is also called as the law of conservation of momentum. Now let me give you two examples to illustrate Newton's first law of motion. For the first example, consider a car that is not moving. It has two forces acting on it, the downward gravitational force and an upward normal reaction from the ground. However, the sum of all the vertical as well as horizontal forces acting on the car is zero, since the normal reaction balances the force of gravity. This is why the car continues to be in a state of rest. For the second example, let us consider a car traveling at a uniform velocity. If you want to continue driving the car at the same velocity, you will still need to press the accelerator of the car. This is because there are damping forces that are acting in the direction opposite to the motion of the car. And these damping forces may arise due to moving parts in the car's engine or the friction between the road and the tire of the car. All in all, to maintain the velocity of the car, the forward force applied by the engine must balance the damping forces acting in the direction opposite to the motion of the car. Now that we understand that an object is inherently lazy, that is, it resists change in its state of motion, a natural question to ask would be, how do we bring about a change in motion of an object? I want you to follow a line of reasoning. Firstly, we observe that the motion is quantified by momentum. And secondly, we observe that if an object is left alone, it tends to resist change in its state of motion. That is, it wants to continue maintaining its momentum. Well then, how do we bring about a change in momentum of the object? We force it to change through an external agent that can cause a change in momentum of the object. And this external agent is the second most important character of this video, and we call it force. Purely based on series of these thoughts, it is not surprising that if force leads to change in momentum over time, then force must be related to change in momentum per unit time. Newton's second law of motion formally establishes this observation, and it states that the rate of change of momentum of a body is directly proportional to the net applied force, and it takes place in the direction of force. This law is incomplete without its mathematical description, and to do so, we consider a point object with mass m traveling in a curvilinear trajectory. At any time t, the object has velocity v that gives you the instantaneous speed of the object as well as its direction of motion. And the object has momentum p, which is equal to the product of mass of the object and its velocity at time t. We take the snapshot of the object at two different instants of time. The first is at time t, and the second is at a later time t plus delta t. The momentum of the object at these two different time instances are different. It is the external force that has brought about a change in momentum of the object at these two time instances. And therefore, as per Newton's second law of motion, the force that is causing this change is directly proportional to how much the momentum has changed over a unit time interval. Now, if you bring these two time instances very close to each other and ask that in the passing of this time, which has been extremely small, how much has the momentum changed? Then in this case, where your time interval was extremely small, the force vector is directly proportional to the derivative of momentum with respect to time. That is, the force acting on the object at this instance of time is responsible for the change in momentum of the object at this instance of time. Since momentum is the product of mass times velocity of the object, for an object with a fixed mass, the force acting on it becomes directly proportional to the product of mass times the time rate of change of velocity. And we define the time rate of change of velocity as the acceleration of the object. And therefore, for an object which has fixed mass, the force acting on it is directly proportional to the product of mass times its acceleration. We have not yet defined the unit of the force vector, and this gives us luxury to pick the value for the constant of proportionality, and we make an obvious choice by picking it to be 1. Therefore, you can write Newton's second law of motion as force is equal to mass times acceleration. The unit of force is named after Sir Isaac Newton, and 1 Newton is the amount of force required to accelerate an object with a mass of 1 kilogram by an amount of 1 meter per second square. We now make some very crucial observations about Newton's second law of motion. Firstly, we observe that it is a cause and effect relationship, where force is the cause and its effect is to bring about a change in momentum or to accelerate the object. Secondly, in statics, when an object is either at rest or traveling at a uniform velocity, its acceleration is 0. And therefore, when the object is in static equilibrium, the sum total of all the external forces acting on the system is 0. And thirdly, Newton's second law of motion is a vector law. That is, the force acting on the object can have 3 effects. Firstly, it can lead to change in the speed of the object while keeping the direction unchanged. Secondly, it can lead to the change in direction of the object while keeping the speed constant. And thirdly, it can lead to change in both the speed and the direction of the object. Fourthly, the Newton's second law of motion discussed in this video focuses on the point object with a mass of m. However, this can easily be extended to a system of particles or rigid body that are not only subjected to linear motion, but are also subjected to rotational motion. And finally, Newton's second law of motion is a local law. That is, the acceleration of the object here and now is determined by the force acting on the object here and now, and not by the history of motion. Now that we understand the relationship between force and momentum, it is time to go to our final question. What is the origin of force? The external force on the body always arises due to other body. Let us look at the implication of this statement. Let us consider a pair of objects, an object A and an object B. Let object B apply a force on object A, and now the question arises that does the object A also give rise to forces on object B? Well, as it turns out that the object A also applies an equal and opposite force on the object B. Let us now consider some examples of this observation. When you sit on a chair, you exert a downward force on the chair, which pushes back against you with an equal and opposite force, allowing you to remain seated. When you ignite a rocket engine, the hot gases produced by the engine pushes against the rocket with an equal and opposite force, causing the rocket to lift off the ground. When you swim, your arms push against the water, and the water pushes back against your arms with an equal and opposite force, allowing you to propel yourself through the water. Finally, let us consider the example of gravitational force. A stone like this one always comes down towards the earth. That is, the earth is pulling the stone down. But does it also mean that the stone is pulling the earth up? Well, as it turns out that the stone is pulling the earth up with the same force as the earth pulling the stone down. But the effect of that force on the planet Earth is negligible because Earth is massive, and therefore you don't see any change in the motion of planet Earth, whereas the stone, which is much lighter as compared to the planet Earth, comes down. This brings us to Newton's third law of motion, which states that for every action, there is equal and opposite reaction. That is, if one object applies a force on another object, then the second object applies an equal and opposite force back on the first object. We make 2 crucial observations about Newton's third law of motion. Firstly, we observe that there is no cause and effect relationship in Newton's third law of motion. That is, an action does not come before reaction or vice versa. In fact, both these forces can be used interchangeably, and they only represent pair of forces. That is, a pair of action and reaction, or reaction and action, it doesn't really matter. The second observation is that the action and reaction forces act on different objects. For example, let us consider the interaction between these two objects, an object A and object B. And when this interaction occurs, the object B pushes the object A towards my left, and on the other hand, the object A pushes the object B towards my right. We notice that these are two different forces since one acts on object A and the other acts on object B, and you can call either of these forces a reaction and the other becomes action, or vice versa. If we consider the motion of only one object, then only one of these forces is relevant. It would be erroneous to consider both action and reaction acting on the same object and claim that the sum of action and reaction acting on that object is zero. This is because only one of these forces act on each object, A or B. In this video, we tried to understand Newton's laws of motion like a story by asking a series of connected questions, one leading up to another. Our ultimate goal is to understand motion, and therefore the first question that we wanted to learn about was how do we quantify motion? And that is when we introduced the first character of the video, that is momentum. Momentum quantifies the amount of motion contained in an object. And since Newton's laws are about motion, the second question that we asked was about what is the natural tendency of the object towards change in its state of motion. And as per Newton's first law of motion, an object resists change in its state of motion by virtue of inertia. And this leads us to our next question on how do we bring about a change in state of motion of an object. And that is when we introduced force in the picture. We require a net non-zero external force to bring about a change in state of motion of an object or to change the momentum of the object. And Newton's second law of motion connects the cause force with the effect, that is change in momentum. And the final question we asked was what is the origin of force? And we realized that external forces always rises from some other body. And these external forces always exist in pair of an action and reaction. And as per Newton's third law of motion, for every action, there is equal and opposite reaction. And this completes our discussion on Newton's laws of motion. I really hope you enjoyed the video, and if you learned something new in the video, please give me thumbs up and do not forget to subscribe for more upcoming content like this. Till we meet again, more power to you.